Hello, and here we are for our second science lesson this week. Now, the first one, as we talked about our live session, was all about trying to explore ways in which you could test the strength of paper or a selection of paper at least. And what we're going to do today is we're going to think about how we might use that or write it up. And I'll show you a way in which you could test it if you're unsure, and then you can actually do the experiment and copy it out yourself. So, can I investigate the strength of materials is our aim by the end of the lesson. And things that we need to think about. So can I make a scientific prediction? Can I explain how to keep a fair test? And can I record my findings and make a conclusion? So when we're writing up a science investigation, these are the things we have to think about. First off, when we're making a prediction, it's not just something that comes out of our head. It is related to knowledge that we might already have, and using that to guide us in our prediction. We talked about having a fair test before, but we need to explain how we're going to keep it a fair test. Part of our method is our way of showing how it is a fair test, and it's not just us trying our ideas out. And thirdly, we're looking at recording our findings, but not just recording them. What do we know from our findings? What do our findings tell us? So, the last lesson, you were set a challenge of testing the strength of different papers. We're going to look at how you would write that test up and go through an idea of how you would test them if you're unsure. Obviously, if you're going to write up yours, you write up what you did, or you can follow this and write that one up and find out what your results would have been. So what you'll need in order to write it up is you need a question. Whenever you do a science investigation, you use a question that is the core of what you're trying to find out. In theory, whatever investigation you're doing, the idea of it is to answer this one question. If you don't have an aim, you don't have that question, we normally call it an aim, then your investigation really doesn't have a point to it. The idea is that the results should help you answer that question. Now, it's not always the case that it will, but it should aim to. Then you need a prediction. So what do you think is going to happen? And this is quite an important one because majority of the time you have what's called a hypothesis or a prediction, which is what you're trying to test. You know what your question is, you have an idea of what your answer is, but what you're testing is to see whether you're right or wrong. And if you're wrong, why? Then you've got a method, and this quite often includes diagrams, because diagrams make it much, much easier to understand what you have to do. If you can show an image of it, then people tend to find it a lot easier to understand what they've got to do. So it's what you did and how you made it fair. Then you've got your results, and that is what you observed and what you measured. This is quite often recorded in tables and then maybe related to a graph if it helps show people what the results mean. Sometimes taking data or looking at data just from a table can be quite confusing, and some people struggle to do that. Whereas graphs, because they're visual, they're easy to see, quite often are used in order to show the information, because it's very easy to see what the results are showing. And they have a conclusion, and that's what you found out. And this answers that question, the aim that comes at the front. Quite often your conclusion explains what your results mean. So my results show me that, and quite often is linked to scientific thinking. So they show me this, and this is because of this. And that's what a high level conclusion happens to be. It not only says what the results show you, but why you think it was that case. Okay, so the following example was for my investigation, and yours might be different, but you can copy the format, but you can write about your own test that you did. Obviously, if you want to follow these and test it out yourself, you're more than welcome to. So my question, from a sample, which type of paper is the strongest? Now we have to say from a sample because I don't have every single paper type there is. So I can only say it's from the select sample that I have. And that's why the question has to be phrased quite particularly in order for you to know that it's not every single type of paper. You haven't gone out, bought all the different types of paper there is, there are quite a few, and test every single one. What you've done is test from a select sample. Then you've got your prediction. So from my sample, I think the cereal box card will be the strongest. And if you're good, you can actually say because. So I think for my sample, I think the cereal box card will be the strongest because it seems to be the thickest. And that's just so that we know what we're talking about, what the reason for it is. And this should always be done before you do the actual test itself, so that you have something to test. Then we've got our method. And this is a set of instructions that somebody else can follow in order to do the same test you've done. They should be able to step it through and do exactly the same thing you do and come out with the same results that you've got. Now you can think back to when we wrote our instructions for Matilda. I said the level of detail you need and how it's done to get an idea of how your method could be written. So you can draw a diagram to help explain or use pictures. So to keep my test there, I cut all the samples of paper to the same size, and I've been explicit on my size, 12 centimeters by 3 centimeters. I taped a paper clip to the bottom, 1 centimeter, to act as a hook for the weights, and held the top 1 centimeter between my fingers. This left 10 centimeters of paper to be tested. And the reason for that is that the point at which your paperclip is on the bottom, it's not going to start pulling to the top of the paperclip. So the whole length, whatever the paperclip is covering, is not going to be pulled in the same way. And the same with the bit you're holding by your hand. The bottom of your hand is where the tension goes, so it's the bit in between that you're testing. Onto the paperclip hook, I placed a fabric bucket to hold weights. You could use a plastic bag or anything else like that, but you just have something that can hold some sort of weights. One by one, I placed pebbles into the bucket until the paper ripped. I recorded the number of pebbles needed to rip the paper. And you might need to think about what size your pebbles were and whether you did that the right way. You could number them, so you always put them in the same order, and that way you know that it's as fair as you can possibly get. If you had a set of weights, you can use that, but you have to use what you have available to you. And I put the pebbles in the bucket in the same order to make the increasing weight the same each fair. So here are my strips cut to the right length. That's me taping my paper clip to the bottom and holding it to the top. Then a fabric bag hook on the end, and if you don't have a bag like this, you could use a plastic bag. And then the pebbles that I'm going to put in the right order. Some sort of diagram to show using pictures also works. So the result is where you show whatever you're recording. So this is quite easy. So you can be showing a table or a graph. It's up to you. Quite often it's recorded in a table and transferred into a graph. So you'd have type of paper, whatever it happens to be, and then what you're changing. So this one here, the type of paper, is what you're measuring, is what you're testing. This one here is what you're changing. And what you're changing is the number of pebbles it takes for that piece of paper to tear. So the number of pebbles is the changing thing. Yeah? So this is the independent variable, this is the dependent variable. Independent variable, dependent variable. And that means that we can then put it into a graph. So we have number of pebbles up the side here, and we have our types of paper here. And then you just put the bars up to whichever number they were at. And you can do this on squared paper, you can do it on lined paper. The one thing to remember is, as you can see from this, our bars aren't touching. And the reason for that is that toilet paper is in no way linked to kitchen roll, in the case of you can't have an area between the two of them which is half of one, half of the other. They are two distinct objects. Because they're two distinct objects, the bar that comes from them needs to be distinct as well, needs to be separate. It would only be the case if you're looking at something like rainfall per month, that the rainfall does link from one month to the other, that the bars would touch. In this case, they're separate objects, discrete data, so they have their own bars, which aren't touching. Finally, we need to do a conclusion. So from my sample, I found out that cereal box was the strongest type of paper. Again, much like our prediction, you could write a because statement in order to show it, because the paper that was in the cereal box was much thicker, and therefore it could take more weight before it ripped. And then your task. On a piece of paper, can you write up your investigation, whether it's similar to ours or whether it is your own version, that is fine. But it needs to include the question, which is the aim, what are we trying to find out? A prediction, what do you think will happen? Your method, include a diagram to show what you did and how you made it fair. Your results of what you observed or measured in a table and a graph if possible. And then your conclusion, what do your results tell you? What did you find out? Does it answer your question? Have a go, see what you can do, and I'll see you in the next video. Goodbye.